So this is Unit 6 in Eltn 132, Karnoff or Kmaps, depending on how you pronounce it. Often it's just abbreviated Kmaps. And we've already looked at a couple of ways of reducing and optimizing digital logic circuits using Boolean algebra and De Morgan transforms, and just even looking at circuits and figuring out ways to reduce them. In this case, we're going to use a very systematic method that's a very visual method, and we basically can reduce either a 3-input circuit or a 4-input circuit and with known outputs, and reduce it down to a smaller number of gates. And so that's what we're going to be doing in this process. So this box represents some kind of logic circuit that has a number of inputs and, in this case, a single output. And we're going to have a truth table here that's going to be populated with all of the inputs. In this case, it'd be a 4-input system. We'll jump around probably back and forth between a 3 and a 4-input system, and a single output X. So all of these outputs are going to be defined for you. This is not a design process per se, or I should say it's not a complete design process, because the outputs in this case will already be defined. It's for some kind of logic circuit. It could be anything from like the examples we've talked about with airplanes and landing gear, or it could be a logic system for a car, audio system, almost any number of devices. But the point is, again, that we're going to try to reduce this circuit so it's using the smallest number of gates. So what is a Kmap? Well, Kmap refers to this diagram right here. And what it's basically we're going to do is remap all of the values, the inputs and the outputs for our truth table into this map. And the whole point of this is that we're going to try to find where we have what are called redundancies or don't care states. So, for example, let's say we have a 1 here and a 1 here, okay, on the outputs based on these input combinations. If we take a look at this, 1 is high, B is low, and C is low, and we have a 1. Here we have A is high, B is low, and C is high, and we still have a 1. So what does that say about C? It's basically a don't care. It doesn't matter if C is 0 or 1, the output will still be 1 based on the fact that A is 1 and B is 0 in both of these conditions. And this is really the key to understanding what a Kmap does. We're going to put all of these values and arrange them in a way so we can easily identify where the redundancies are. Now, to make this work, what we have to do is create an arrangement on this Kmap of all these variables. The A and the B on the left side here represent inputs that we're going to show as 1s and 0s on the left. The C, and each one of those are going to represent a column, or rather a row here. C is going to represent 2 columns, a value of 0 or 1. So let me show you how this works. We're going to start with A is 0, B is 0, and C is 0. And what that does is it maps this location here, A, B, C, to this particular cell. Okay, so let's say, for example, that that's a 0 in that case. The output is 0. We would write a 0 in that cell. Now, what we're going to do is continue to write these in, well, what looks like order at first, but then it gets a little weird. We're going to 0, 1, then we're going to write 1, 1, 1, 0. And since C can only be 0 or 1, we'll write 0 or 1 there. Now, the reason that we're writing it kind of out of binary sequence, we're used to counting in binary, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. But you'll notice that this sequence, it's not really in order, it's jumping out of order. But the reason that we're writing it that way is because we only want to have one transition between any row as we're going from this row to this row to this row. We only want to have one bit that's changing at a time. So in this case, going from this row to this row, the B changes from 0 to 1. On this row to this row, A changes from 0 to 1. If we'd written it the other way, where we have 1 and 0 here, you'd have 2 transitions occurring at the same time. And we'll see why that's important. So I'm going to go ahead and fill in the rest of this map with some values, and then we'll go ahead and map the rest of the locations in the Kmap. Okay, so I've just filled in some random values here as an example of how this works. So what we're going to do is systematically fill in the Kmap with the values here. And I'm using blue as outputs here in this case, and the reds as the inputs. So 0, 0, 0 we mapped there. 0, 0, 1, where is that located? Well, A and B are 0 here and here. C is 1 here. So we're going to map that value over to here, which is a 0. The next one is 0, 1, 0, which is here. 0, 1, 0 for A, B, and C, and that is a 1. And 0, 1, 1, 0, 1, 1 is a 0, so we're going to put a 0 there. And now we're jumping ahead a little bit. 1, 1, 0 is the next row here, and that's a 1. And then 1, 1, 1, which is a 0 here. We'll put in a 1 there. And then we have A is 1, B is 0, C is 0. That's here. A, B, and C is 0. So that's a 0 there. And finally 1, 0, 1. That's located here. And we have a 0. Whoops, I wrote a 1 there. That should be a 0, right? 1, 1, 1 should be a 0, my bad. Okay. So now what we've done is what's called mapping all of the output values to the Kmap. And what we're trying to do here is identify wherever we have redundancies. And really it's, I don't know if redundancy is the best word, but a don't care is a common way that they express this. So where do we have the situation where we have a don't care? Okay, well that's where we have two cells in this case that are adjacent to each other. So we can see here that whether, in this case, B and C are 1 and 0 here, 1, 0, 1, 0, and it's 1, and A is changing from 0 to 1, so we don't really care about A. So what we can do is group those terms together and then find a way that we can then express that without that A variable being included. So the final step in reducing the circuit is, again, looking at any conditions between these two cells where something transitions. So let's take a look at C, for example. In this column, between this point and this point, C is 0. So it doesn't change. Between these two, the value of B does not change. It stays at 1. But A is transitioning. So what that means is we have to throw it out. And to write the final equation, what we do is look at the variable, in this case B, and see what its value is. It's a 1, which means it's true. So we would write X equals B, okay? But then we're going to also look at what the value of C is in this case. C is 0. So we'd write this as B, C, naught. And that would be the complete circuit. If we drew it like this, where we have an input B, and it's inverted, or it's not inverted, sorry, I'm looking at the wrong one there. We look at B, but C would be inverted. And this basically is going to AND these terms together. Now, this is only one term here. Sorry, that's a crummy looking AND gate. Let's try to fix that a little bit. There we go. We only have one term here. In other words, we only have one grouping. So we only have one what are called min terms. If we had multiple overlaps, ones in different locations that could be grouped together, we would then OR those terms together. And that's what I'm going to do in this next step. But before we do that, I want to try to identify what the different ways that we can group these ones together. So that first example, we had these two ones in adjacent cells. Another way we can have adjacency is by having ones here that would group together. Now what's important though is to see what is transitioning there. A is 1, B is 0, but C changes from 0 to 1. So what are we going to do with the C? We don't care about it. It doesn't affect the circuit, so we throw it out. So how that'd be written though for that grouping would be A and what? Since B is a 0, we'd write it as B naught. And that would be our circuit. Okay, let me take a look at it. Let's do a couple other examples here. Now this is what's a little bit weird about this, is that if you take a look at this, trying to get that out of the way there, if we take a look at this as being kind of like a piece of paper that you could curl around behind itself, we can also have adjacency between this cell and this cell. Kind of weird. But if you take a look at it, C is 0, B is also 0, but A transitions from 0 to 1. So what would that be? If we have B is 0, it would be B naught. And C is 0 in that column, C naught. And we can do that also from these two cells. So there are multiple ways that we can identify two. Now, if we only have one term, that doesn't gain us anything. We're not doing any reduction there. But, as you probably may have figured out at this point, if we have 4 cells grouped together, we can reduce things even more. Now, when I'm writing the ones here, it's assumed that there's zeros in all the other cells. But let's take an example here. Let's say we have 4 ones here, and the other terms here are 0. Now, I'm not mapping this from this truth table here. I should probably wipe that out, because I'm just kind of picking up some kind of random examples here to look at. So I'm gonna wipe those out so those won't cause any confusion, hopefully. I'm just giving examples of how things could be mapped. So now in this case, let's take a look at this. We're always grouping in powers of 2, by the way. So 2, 4, or 8. If it was 8, if all of these were filled, it'd just be a wire. There'd be no logic really going on in it. Well, let's take a look at this situation. Okay? What we have to do is look at going from, now in this case, because we have 4, we have to look at going from the rows, top to bottom, and also the column left to right. So let's see what we have here. If we look at these rows going from the top to bottom, we have A is 1, B is 1, A is 1, B is 0. B transitions, it's a don't care, so we throw it out. So we know we have an A here. Now here, if we're looking, we also have to look from left to right, going from the columns. But here, if we go from this column to this column, all we're looking at is C. And C transitions from 0 to 1. So what does that mean? It's a don't care. So in that case, if we have those 4 cells filled, it's simply the term A. That's all it is. That would be what our circuit would be. And really what that ends up being is this. A is mapped to X. B and C aren't included, so we're simply taking that input and tying it directly to the output. And that's pretty unusual. Most of the time there are more other ways that we can map these. Now, let me give you another example here, and I think you'll start to see how this can work. We can also have combinations of groups of 2 and 4. So for example, if we had a 1 here, well, we had A already as one output, or one input rather. But what else could we group here? Well, remember that this can curl around on itself. So we can also, we've grouped these 4 together, but we can also group this one and this one. Now, because we have 2 terms now, we have to have an OR. We're ORing these 2 different terms. And let's take a look at what's changing here. First of all, is A changing? We're going from this row to this row. And A is changing. It's going from 0 to 1. That means it's a don't care. We'd throw it out. Let's take a look at B. When we go from this cell to this cell, B is 0. So we'd write that as B naught. And how about C? C is a 1 in that column. It's not changing when we go from that cell to that cell. So how we would write that is A or B naught and C. So one of the things I'd like you to do is to be able to kind of fill in random cells, and we'll do this as a homework exercise, and with groups of either 2 or 4, and see if you can identify what the different values are. So this is basically a 3-input Kmap, and I hope that this process is becoming a little bit more clear. It may take you a few times to kind of go through it to understand exactly how everything works, but you'll see that the same process applies for a 4-input Kmap, which we'll do next. Okay, next we're going to look at a 4-input Kmap. Now, in this case, it's very similar, except we're simply expanding another input here D in this case. And the same process for mapping, it follows the same process as for the 3 input. So for example, this first row here, A, B, C, and D, where all 4 are 0, well, that'd be A, B, C, D are all 0, so that would represent that cell. Cell 0001, if that was a 1, or whatever value that is, we'd write that into this cell. Now again, you have to be careful here because we jump. Now we go to 0011, and that's located where? Well, it would be this value here. And let's just take a look, for example, at the very bottom right corner cell, 1010, that would end up being this cell here. So you have to make sure if the mapping isn't done properly in the first place, you can run into problems pretty quickly, as you can imagine here. Now let me show you some differences with the mapping in this case. Let's say, for example, that we have 2 cells here that are 1. Those are considered adjacent because in this case our map is going to fold around this way. So those would be considered adjacent cells. What would the value of that be? Well, in this case, in this row, A and B are 1 and 0. They don't change. And C and D, C is 0. But if we go over to this column, it becomes 1. But D stays 0. So how we would write that equation out is, in that row, A is 1, so we'd write A. B is 0, so we'd write that as B naught. And then C transitions from 0 to 1, and so we throw it out. But what is D? D is 0 here, 0 there, so we would write that as D naught. The rest of them follow the kind of same process. But let me show you a couple of oddballs. We can actually have these 4 corners mapped. And in that case, what you have to do is look at the transitions between here and here, here and here, and also from left to right. Okay? Anytime you have 4 terms together, that ends up giving you a 2-term value. As we get more and more 1s populated in there, we end up getting more or fewer terms in the final equation. So let me go through an example here, or let me show you a couple other real quick exceptions that are kind of different. Let's say, for example, we had something that mapped like this. We had a 1 here and a 1 here and a 1, all by itself. Okay, and that happens sometimes. So let's take a look at this one to start with here. Get my eraser sock out of the way. Okay, in this row here, A is 0, B is 1, so we'd write that as A naught B. And then what happens here? C transitions from 0 to 1, so we would throw it out, but D is a 1 between those 2 points. So we'd write that as A naught B D. Now how about this cell here? It's all by itself. It has no other cell adjacent to it. So in that case, it'll end up being a 4-term, what is called a minterm. So we'd say or, nothing's changing here, so we just write it out. A is 1, so it's an A. B is inverted, so it's B naught, B is a 0. C is a 1 here, so it's a C. And then D is a 0 there, so it's D naught. So that doesn't reduce to a whole lot because we got that 1 term all by itself. If we group multiple cells together, we can eliminate them by that same process. So let me go through an example here and we'll see if we can kind of put it all together. Okay, so I'm starting with this truth table. And that's been defined by whatever our design criteria is, whatever the system is that we're trying to convert into a digital logic circuit. What I've done here then is mapped all of these values over to our Kmap. So for example, 0000, which would be this one, is a 0. 0001 is a 1, so we'd put a 1 there, and so forth. And I've mapped this all out. Now if you want to pause and take a look at that and make sure you understand it, that's fine. I want to make sure that as we go through these steps, if we make a mistake along the way, things don't end up working. So we have to be careful here. Now, once we've got these together, we can start to group them. And we want to group the largest set to begin with, and then work our way to the smallest number. So we have 4 cells here that all have 1s in them, so we can group those together. I'm just going to draw kind of a box around them. And we have two cells here that we can group together. So I'm going to draw a box around them. And then we have one that's just by itself right here. So let's start with this big one. Let's start with the rows going top to bottom. A is 0 and stays 0, so we can write this as A naught. B transitions from 0 to 1, so we throw it out. As we go in this column from left, or these columns from left to right, C is 0, transitions to 1. That means we throw it out. But D is a 1. So in that case, we'd write that as A naught D. Let's double check that. A naught, that looks good, and D. Now let's go down, and you'll notice that those four ones reduced to two variable inputs. If we had 8, it would be reduced to a single variable input. Now let's take a look at this one here. Let's go top to bottom. A, in this case, is not changing. So we're going to put an OR there because it's a different box. It's a different group. So we have A. B transitions from 1 to 0, so we throw it out. And then we have, in this column, C is 1 and D is 0, but they don't change, right? So, because C is a 1, it's a C, and then D is a 0 here, so it's D naught. Now, we've got this 1 off by itself. We can't ignore it, but it ends up making a 4-input term. And it's kind of, these ones are a little bit easier because we don't have to look at any don't cares. We have to basically map what the values are. So in this row, we have A is 1, B is 0. A, and because B is a 0, it's a B naught. And then in that column, C is 0, so it's a C naught. And D is a 1. It doesn't change there. And that would be our minimized circuit. Okay, so what this has done for us is identify different positions in our map where we have, for example, in this row here, in this row here, we have a term, a C here, that transitions from 0 to 1 that's a don't care. Now that happens to be included in part of one of the other expressions, so we can't just identify that one. But otherwise, you'd have to somehow systematically look and figure out which ones of these have these don't care conditions, and that's what the Kmap is doing in this case. Now the last thing I'm going to show you here is kind of an abbreviated way of explaining or showing a whole truth table here. And this is kind of and I'll probably use this on tests at some point because it's a lot easier than trying to draw out a whole truth table, but I'll do it at some point. And basically what we're going to do is draw the outputs as what's called a function of x. Let me explain this. So to write this in a shortcut notation, what we first have to do is remember that we can kind of identify each of these rows as a number, as a binary number. And so, for example, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the reason I'm doing this is that we can then say, well, which number has a 1? Because all we really care about in this case is the 1s, is what are called sum of products here. And so, for example, 1 is a 1. So we could write a 1 here. Okay, 3, 5, 7, 9, and 10, and 14. Now to write this more formally, what we could say is something like this. The function x of A inputs A, B, and C equals and this is kind of gets a little funky, the summation of the min terms, that's the summation sign with an M, with all this in parentheses. So if you want to impress somebody with something that looks very complicated, but actually explains what it is, let me write this out a little bit better. So we have f of x of inputs A, B, and C equals the summation of what are called the min terms, which are each of these individual terms, and then we'd have these numbers here, 1, 3, 5, etc. And the whole point of that is it's a lot easier to write this kind of formulamatic way rather than having to draw an entire truth table. Point is, both things mean the same thing. But in order then to populate the truth table, what you'd have to, or the Kmap, what you'd have to do is find out where the 1 is. Where's the 1? Well, that's 0001, which is located here. So it would take a little bit more practice to kind of figure out how that works. But in some cases, you might see that shorthand notation. Now, I realize there's one more example here that I didn't think of, and that's where we have overlap conditions. Let me show you that real quick and we'll wrap up. Let's take a look at this situation. Here we have 6 cells that are basically adjacent to each other. Sorry about that. Let me fix that. But you cannot group 6 cells together. It just simply won't work as far as for example, if we looked at this column here, B goes 1, 1, 0. Well, what would that be? It doesn't really make sense. So what we typically do there is group the largest sets, so we can actually have an overlap here, where we have this group and this group overlapping. Now, we could have also done it as this group of 4 and just these 2 terms. Ultimately, it doesn't make a lot of difference in the circuit. But if you can overlap cells, that's an advantage to actually mapping the cells. Okay, I'll leave that as an exercise for you to go through that process. So that's kind of an introduction to Kmaps. This is going to be kind of one of the last subjects that we have related to gate reduction. There are certainly more advanced ways of doing this. Typically it's done with software, but there are other ways of doing. For example, if we went to a 5th input, what do we do? Well, it's kind of weird what you end up doing, and you can do this with Kmaps, but it's really kind of funky. What you do is you end up making a Kmap on this level, but then end up making a Kmap above it. That would be your 5th variable. And then you start mapping values from the top down to the bottom also, if you can visualize that. So basically you'd have a Kmap here of those 16 values, and then you'd have in 3D space a Kmap on top of it. And then not only could you group left to right, but you could also group cells that are on top of each other or in that direction. So it gets, but that's not very practical. Kmaps really don't make a lot more sense for using something larger than 4 inputs. There's another method called Quine-McCluskey, where you get into larger values. But again, a lot of this is done with software. But I've used Kmaps when I've got a simple circuit and I want to try to reduce it pretty quickly. So hopefully, as you go through the homework, this will make sense. If you have any questions, please drop in for office hours or send me an email. I'd be happy to go over it.